So thank you very much for coming. Thank you to Amir and Ivan for organizing the session, and to the general co-chairs, Tarek and James, and the whole committee for organizing this conference. It's been really fun. I too actually am getting over the flu, but I've been taking Tamiflu for like 5 days almost, so I'm over it. I'm not contagious anymore, but I am a little fatigued, so if I pass out, just kidding. Related to both talks, being infected with the flu, the first speaker, and the second talk, studying spread dynamics over graphs. I have been studying spread over graphs, and what I'm going to do is I'm going to introduce some models, and then I'm going to explain how I've been studying these models for a couple of years, and I hadn't seen any validation work done using real data. Like, if we're studying these models, why? Like, if they're not any good, why do we care? So I started looking at some data sets, and I'm going to show one of those in this talk. And if you have any questions, please stop. So studying, as was motivated in the last talk, studying spread in networks is important. We could think of this as ideas in a social network, or the flu in this room, hopefully not spreading. Or we think about on larger scales, Zika spreading across the world, or Ebola. And as system designers, this is very important, because if you have a disease that maybe is starting in LA and New York, and you don't contain it well enough, well, it could get bad, or it could get worse. But maybe you're an advertiser, or you're a politician, and everything going red is not the worst thing to you. So depending on which side you look at this, we have different ways of interpreting what we want to do and what we'd like to drive the system to. In most of my work up to this point, I've been the good guy trying to get rid of the disease and the bad ideas or whatever. But I think it's important to look at it from both sides. And this is not a new problem. These models have been studied for years. The first epidemic model was studied by Bernoulli in the 1700s. But they're still relevant today because we have new systems. We have social networks. This is a real Twitter network. And spread across these networks really can affect things, as we've seen in recent days. And you have network robotic systems, and understanding how spread of computer viruses and things like this are very relevant to how we design systems to be robust and secure. So now I'm going to quickly go through some models and explain some ideas, but it's a little quick because we're running low on time. So if you have a question, please stop, but I will try and give as much depth as I can. The first SIS, or susceptible infected susceptible model, was proposed by Kermack and McKendrick in the early 1900s. And the idea is that you model the population in two groups. A group of susceptible individuals and infected individuals. So susceptible means you're healthy, but you can become sick at any time. And they modeled them as differential equations, where you're positively affected in the susceptible group by a healing rate, delta. And you're negatively infected by an infection rate. And the opposite for the infected group. And note that these nonlinearities here make the analysis more difficult. And it's nonlinear in the state, but we usually have a constraint on the population, so you say S plus I equals N, so then this becomes quadratic in I, or S, depending which side you go. So the idea is that individuals can jump back and forth between being susceptible to infected at a rate beta, or from infected to susceptible at a healing rate delta. And this is the group model, but we can also think of this as a graph model. If we think each agent can be either susceptible or infected, and the transition between those two states for a single agent is dependent on a healing rate delta I, so for agent I, that healing rate, or an infection rate beta I scaled by how sick their neighbors are, that's what this X will represent, and the connectivity to those neighbors. And it's a little low for people on this side, sorry, but the dynamics evolve as this. So the state is the probability of being affected, or if you think of I as a subpopulation, it's the proportion of that subpopulation that's sick. And so it's negatively affected by the healing rate and positively affected by how susceptible you are, and your healing rate, and how sick your neighbors are, and how you're connected to them. Oh, I also forgot to thank the sponsor, Honeywell. Thank you for sponsoring. Yeah, so there's a rich body of literature in this area. So it's been studied for years, as I mentioned, starting with Bernoulli, and many different fields have picked it up, and it has evolved over time. This is one view of the literature. There's been static graph structures by various fields, and then there's been, in this contextualization of my work in this graph-dependent spread. So, yeah. So there are a lot of models that model these true systems, as we'll call it. Let's see, we have some spreading systems. One way to model it is on the left, we're going to see continuous time, and on the right, we're going to see discrete time. So the first line is showing different ways to model this with 2 to the n states. Tons of states, but it enumerates all the possibilities and shows the probabilistic transition between these states. And there are different ways to approximate these models, because 2 to the n is a lot when n gets big, right? So you can do a mean field approximation over here. You can just truncate over here, getting rid of the higher beta terms when you multiply these out. And then you can also get back to discrete time on this side by taking Euler's method, applying Euler's method to this discrete equation that we saw before. And then we get the exact same model if we let our sampling parameter go to 1. And I think this is interesting because we have the same system we're trying to model. We've gone through 2 avenues, and if we take some approximations, we get the same model. So it's sort of a sanity check, not a proof, obviously, but it shows that maybe we're not doing the worst thing ever. But can we validate with data? That's the next question. And to be able to do that, we're going to do some analysis on this model right here, and then we'll use that analysis to do some validation. So we're going to focus again on this model, and K is our time sample. Remember, delta is our healing rate, beta is our infection, and Aij is our network structure. And we can rewrite this in matrix form, and the nonlinearities are hidden by this diagonal matrix X of K. We have the Aij's in this A matrix. The D matrix is the diagonal matrix with the healing rates, and the B matrix is the diagonal matrix with the infection rates. Okay. And all this work has been accepted in special issue of Control Systems Technology. So we're going to make some assumptions on the model for it to be well-defined, the top ones to be well-defined, and the bottom one to make the analysis be pretty. So the initial conditions are sensible. We're saying that our states are in between 0 or 1, where our probabilities or our proportions are sensible. The second assumption is saying we have non-negative healing and infection rates and connectivity between the agents. And then this third assumption is constraining it's pretty much constraining the sampling parameter so that you don't jump too quick and you don't get out of the bounds of where the model makes sense. Because you want it to be a map between 0 to 1 to 0 to 1. And then we're going to assume that the BA is irreducible, which is saying that the underlying graph is strongly connected. So if it's not, we can just treat it as 2 separate systems, and we can analyze the 2 systems separately. And then if A20, it just doesn't make sense because you'll be stuck. So the first result is saying that if the spectral radius is less than or equal to 1, then the healthy state, or where everyone is at 0 and no one's sick, everyone is healthy, the healthy state is asymptotically stable. And then the next result is saying that if it's strictly greater than 1, then this system that we're studying has 2 equilibrium. It has the 0 healthy state and some epidemic state, where this notation means that every entry is strictly greater than 0. So everyone's at least a little sick. possibly a little sick. And with this flu epidemic, I'm going to get my hopes up. So just a quick sketch of the proof ideas that we use here is we're using the Perron-Frobenius norm for irreducible Metzler matrices. A Metzler matrix is pretty much where all the off-diagonals are non-negative. And a Perron-Frobenius is showing that is a relationship between the maximum eigenvalue and the corresponding eigenvector, showing that it'll have this form. And we use a fixed point argument using this pretty mapping right here to show that under this condition, there's a contraction mapping towards this equilibrium as long as you don't start at 0. And then we use the fact that this is a fixed point to show that this rate of change in our difference equation is 0. And then we show uniqueness of this equilibrium by assuming there's 2, and with a straightforward argument showing that they're equal. So a result of this proposition and the first theorem is that this is a necessary and sufficient condition for the equilibrium of the healthy form we'd like. And a corollary of these shows that if we know the state where you end up and you know the graph structure, you can exactly recover the proportion of the healing rate to the infection rate. And this is what we're going to use. We have some validation results, some identification results in the paper, but this is the one we're going to use on this data set because we don't have time series data. We just have the final state. So in my last couple minutes, I'm going to try and whiz through these. So John Snow was a physician in the 1850s in London. And at the current time, cholera was thought to spread through the air. He knew this wasn't true. So what he did is he mapped out one cholera epidemic in the Soho district of London. He took this map and drew a little rectangle for each death. So big rectangle means lots of deaths. And he did it to show that this pump right here was the source of the epidemic. I'm supposed to have a yellow triangle, and I forgot to add that. But the idea is, if you notice, all the deaths are centralized around that. You have other pumps on the edges, but those weren't infected. So the deaths are all centralized around here. And he took this to the officials, the government officials, and were like, look, the deaths are coming from this pump. The water's infected. Trust me. And they were convinced enough to remove the handle of the pump. Several days later, people stopped dying completely. So it's pretty much the beginning of modern epidemiology was his work here. And here's a digitalization of that data set. So the red means sick, like in the previous image. Blue means healthy. This is the final state. So we're assuming this pump is infected, and that the diameter of the circles is scales by the number of deaths per household. And he also recorded how many deaths per day there were in this area. And we can digitalize that and see per day how many deaths happen. And what we're going to do is we're going to take an initial condition. We're going to assume that only the pump is infected and everyone else is healthy. And we're going to play with the graph structure. And the state of the system, the epidemic equilibrium, is going to be that plot that we have. That is the number of deaths per household. So the first graph structure that we're going to try out is just kind of the naive approach. If it was spreading through the air, as was commonly believed at the time, then it would kind of be spreading kind of equally among neighbors. So we're letting, if they were close enough, they're connected. So it looks like this. This is the R was chosen the smallest number such that everyone is at least part of the graph is that the matrix is irreducible. So if we do that and we simulate it, we get this behavior. Remember, this is the true data, and red is how it works, how the system works. And as we suspect, it doesn't work very well. But if we try several different graph structures, we can get much better behavior. We know that the pump was the source of the epidemic. So if we add a star graph on top of that, so we're allowing the pump to affect every single household, so it looks like this, the green edges have been added, then we get a much better picture of the behavior of the system. And the red is the simulated, and the blue is the true. And then for the final attempt, we chose heterogeneous household sizes. So we changed, we didn't make them all the same size, and using some census data compiled by a different paper. And then we removed all the edges in between the households except the self loops. And then I'm running out of time, so I'm just going to show you what the graph looks like. This is what the matrix ended up looking like. And this is what the graph structure looks like in picture form. And when we simulated it, it's even prettier. And it's exactly what he thought. The pump was the source. It was affecting the people. And yeah. So I have a simulation where it shows the time series. And it's not perfect. This is probably not exactly how it's spread. But it is capturing the behavior. And it seems to do a pretty good job. And therefore, studying these models with graph structure is important and not a waste of time, at least in my opinion. So I think I'll just finish on time. So I have future work and stuff I'm doing, but yeah, let's let someone else talk. Thank you very much. Yeah, Rafael.
So I'm wondering the assumption that you made at the beginning, which is that. Thank you. This is sort of a question about the model that you're using, this SIS. The assumption that you made at the beginning is that people, once they heal, they're still susceptible. But in a lot of epidemics, you become immune to the disease, and so you're no longer susceptible. So my question is, how does this change the model? Does it just make the nonlinearity more complicated because you don't have this constant population size, i.e. S of t plus I of t doesn't equal n anymore, or is it even more complicated than that?